In this video, we will use our understanding of conditional probability to develop something called the law of total probability. So to understand the law of total probability, let's think about two events. We'll call one A and one B. So here's our sample space, and here's a little picture. This part of our sample space is A, over here is A complement, and this oval is B, and then anything outside of the oval is B complement. Okay, so if we want to know what's the probability of B, well, we can look at the part of B that intersects with A, and then the part of B that intersects with A complement. So the probability of B is equal to the probability of B intersect A plus the probability of B intersect A complement. So we kind of understood this before, but now we can take it one step further and talk about it in terms of conditional probability. So based on our definition of conditional probability, we know that the probability of B intersect A is equal to the probability of B given A times the probability of A. And similarly, we can rewrite this as the probability of B given A complement times the probability of A complement. So here we calculated the probability of B by splitting B into the part that intersects with A and the part that intersects with A complement. But if we wanted, we could calculate the probability of B, so let's have this be B, by taking our sample space and partitioning it up into a bunch of events. So not just A and A complement, but we could have several events. So maybe here's A1, A2, A3, A4, A5, and A6. So we could do a similar thing here. The probability of B is equal to the probability of B intersect A1 plus the probability of B intersect A2 plus the probability of B intersect A3 plus the probability of B intersect A4, blah, 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 all the way to the probability of B intersect A6. And then we could write each one of those intersections using our conditional probability. So if we want to write that out, then we could say we're going to let AI, this set, AI from I equals 1 to n, be a set of events partitioning S. So what partitioning means is that if we take any two of these events, they have no overlap. In other words, their intersection is 0, as long as we're not looking at like the intersection of event with itself. So if we look at two different events, they have no overlap. And if we look at the union of all of these events, it equals the sample space. So just like we drew here, this is one example of a partition of our sample space. Then for any event B defined on our sample space, we can calculate the probability of B by summing up the probability of B given AI times the probability of AI from I equals 1 to n. All right, so let's apply this law of total probability to an example to see how it can be used. So probabilists love talking about urns and balls. So here's urn 1. It has 2 red balls, 4 white balls. Urn 2 has 3 red and 1 white. Okay, so imagine that we have urn 1, and we draw 1 ball at random from it and put it into urn 2. Then we go over to urn 2 and draw 1 of the balls out at random. So we're wondering, what's the probability that the ball that we draw out of urn 2 is red? So lots of times when it's appropriate to use the law of total probability, people will say, well, the answer depends. And you're right. The probability that the ball drawn out of urn 2 is red depends on what happened, what color we drew out of urn 1. So since it's dependent, we're going to use this law of total probability. So let's define some events. B is the event that the ball drawn from urn 2 is red, and then A1 is going to be the event that the ball drawn from urn 1 is red, and A2 is the event that the ball drawn from urn 1 is white. Okay, so if we just rewrite this over here, then the probability of B is equal to the probability of B given A1 times the probability of A1 plus the probability of B given A2 times the probability of A2. So that means we need to find these 4 probabilities. Probability of B given A1 times and the probability of A1. We need to find the probability of B given A2 and the probability of A2. All right, so it's probably easiest to start with the unconditional probabilities. So if we want to know what's the probability of A1, in other words, we're asking when we are just starting with EARN1, what's the probability that we draw a red ball from it? So EARN1 had 2 red balls and 4 white balls. Therefore, the probability of drawing a red from EARN1 is just 2 out of 6, since there are 6 total balls. Similar thought process for calculating the probability of A2. If we want to know what's the probability that the ball drawn from EARN1 is white, well, there are 4 white balls out of the total of 6, so we have 4/6. Okay, so the unconditional probabilities, those are figured out. Now we can think about our 2 conditional probabilities. Probability of B given A1. So the given A1 part means that we had taken a red ball from EARN1 and put it into EARN2. So if we put a red ball into EARN2, then that means that now we have 4 red, 3 plus the 1 from EARN1, and 1 white. So we have a total of 5 balls now in EARN2. 4 of them are red, so we have 4/5. All right, so probability of B given A1 is 4/5. We use a similar thought process for probability of B given A2. If we had put a white ball from EARN1 into EARN2, then that means that EARN2 now has 2 white balls and 3 red balls. So the probability of having a red ball is 3 out of 5. So now we have the 4 probabilities we need. We can just go ahead and plug those in, and we get 4/5 times 2/6 plus 3/5 times 4/6, which comes out to 2/3. Okay, so in this sort of example, it helps to be organized about what information you have and how to define the events. So you can notice that we wrote out the number of balls in each EARN and how many colors there are of each. And then we defined our events so that it would match up with what we were familiar with before.